I want to talk today about analyzing cacheline contention using perf c2c. The motivation for this is that in Postgres 14, I landed an improvement to make snapshots more scalable in Postgres, and a lot of that was to avoid cacheline contention. And I told people of how I noticed that there was this cacheline contention, and yet nobody really understood what I said when I said like, oh, I use perf c2c, and a few people tried it out and they're like, I don't know what any of this does. And they tried to read the documentation, and the documentation is somewhat minimal or unbalanced. So the goal here is to explain that process to some degree so that others can get started. And the main type of issues you would analyze with perf c2c is like if there's like false sharing going on cache lines, or if there's contention on cache lines. It does require some hardware understanding. I will do the first third or so of this slide. The talk will be about trying to explain the minimum required to understand a bit like how any of this works on a hardware level. And what's very important to understand for that is basically how is like memory structured, or how are the various caches structured over the memory, and then how are all those caches kept coherent with each other. On a modern CPU, we have like 3 levels of caching typically. There's L1, which is like the very, very fast, but very small, because it's very expensive to build in like area. And once you make it bigger, it also gets slower. And that's like on the order of 1 nanosecond delay to access it. So like on a CPU, that will be, I don't know, 3 to 5 cycles or something. And there's 2 of them. One is like separated for instructions, and we don't really care about that here. There's actually a lot of problems sometimes with not hitting the instruction cache very often in Postgres, but like it's just a different topic. And then there's a data cache, L1, and then above that there's a L2, which is like considerably larger, like on the order of 1 megabyte. There's some CPUs that are like 2 to 56 kilobytes, and I think there's some with 2 megabytes, but something like that. And we're talking about 3 to 5 nanoseconds access times here. And this is all those levels are within each core. And then there's L3, which is like a lot slower, but it's shared across cores. And that sometimes is very important for like how data is transferred between cores and to be able to share state across cores. And below that, obviously, then there's memory, and a local memory access will be somewhere between 60 and 120 nanoseconds to access it. If your memory is not on your local CPU node, it will be slower. There's a lot of details that I'm omitting here. I just don't have the time. Here's, for example, how my own laptop, see in the front, the cache hierarchy looks like. We have like 8 CPUs. And within each of the CPUs, we have like hyperthreads, or SMT, or whatever you want to call it. And they share all the caching infrastructure with like L1 and L2. And then above that, there's L3 that's shared across all cores. In more complex, in like larger machines and server machines, that often will mean that we will have more than 1 CPU or 1 CPU socket. This is, for example, my workstation. We have 2 identical CPU sockets, each with 10 cores and different amounts of cache, but otherwise pretty similar. What this means is that because we now have 2 CPU sockets that need to coordinate all the cache contents, they have to transfer sometimes data from one CPU to the other CPU. And as you can imagine, it will be a lot slower to go from the memory in one CPU socket to the memory in another CPU socket, even if it's already in cache there. Which means that on multi-socket machines, you will often see much higher latencies, which is a price basically to scale that far. You might say that you don't really care about multi-socket machines, but the thing is that in modern, in the current, and particularly in the future, we will have much more socket-like things that are inside one CPU socket. It's gotten very hard to build like these complex CPUs as one with as many cores as one on one die. So what we now do is within one CPU socket, we will have like, for example, in the case of AMD, have 4 pieces that have like shared state, like in this case, Z4 is like for a Zen4 set of cores, another set of cores, another set of cores, another set of cores, and that will then, the latency between within one of these dies here will be a lot smaller than the latency to this die, and even smaller, and the latency to somewhere over here will be even bigger because it has to go across a bus. On Intel CPUs that can, or systems that can be even, there can be up to 8 of these CPU sockets within each, then having, I think, up to 4 subnodes, and that number is likely to increase in the future. With all these different set of cores, it's obviously caches that we here that I showed. One really crucial piece is to keep all those caches in sync as much as we have to do. The one important thing to know for that is that the cache contents are managed in cachelines, which is basically the smallest cacheable unit. Whenever you read something into one of the caches, we don't just read like 4 bytes. If you read 4 bytes, it is 64 bytes, and on some CPUs, 128 bytes. Just because it's too expensive to manage memory on a smaller scale. And the way that all these caches are coordinated to be somewhat correct is a protocol called MISI. And basically that means that the idea is that every cache line has 4 different states. Like it can be modified, in which case like it has contents that none of the other caches have. It can be exclusive, which is that it's not modified, but the core could be allowed to modify it in that moment because nobody else is allowed to have that cache line. And then we have shared, which means that the cache contents are not just present on one CPU or in one cache. It might also be in other caches, other CPU cores, or even on other CPU sockets. Or the cache line might be unused. And as you can imagine, to get a cache line to be in exclusive or modified state, we have to first make sure that no other CPU has, or no other core has that cache contents in shared state, because otherwise we wouldn't be the only one holding it. So that means that whenever you modify memory and that cache line is currently in shared state, we first have to talk to potentially all the other CPU cores in the system to tell them, hey, invalidate this. And which in case that cache line on the other CPU might even, if it wasn't shared, but on the other CPU core in modified state, might have to transfer the contents of the cache line somehow to the current CPU, because otherwise you would lose the modified content. Because if you just fetch the contents from memory, that would lose the lose the update. And on some CPUs, that will happen by the modified cache line contents first being written back into memory and then being read back from memory. Or on more complicated systems, we will move the modified state from one cache to the other cache. And that's more efficient because we don't incur the memory latency, but obviously also more complicated. So what is cache line contention even? And what does false sharing mean? Here I have a stylized picture of a cache line, and part of that cache line is occupied with a lock. And there's nothing else on that cache. If you just assume that we have a lock that needs to be held, that will obviously have to modify the page content, because you have to say some bit or byte or whatever, say that currently this is locked. And obviously that needs to modify the page contents, and for that the cache line contents, and that will have to get the line into modified state. Which means that if you have many cores trying to get the same lock, we'll have constantly moved this cache line back and forth. But that's kind of unavoidable, because that's the fundamental nature of a lock. We have to have proper states to manage that. And it has to be up-to-date state, because you can't just lose somebody else having the lock. A slightly more complicated version of this is that on the same cache line that you have the lock, you also have data that's protected by the lock. And that is most of the time fine, and even a good idea. If you have data that's a lock that is acquired exclusively, and then we just use that to update some shared state and then release the lock, it's good that we only have to touch one cache line, because we don't have to transfer multiple cache lines back and forth. But if you have a slightly different state, namely this one, where we have data that's protected by a lock, but the data is read mostly. That is like, it's not constantly modified. What we then have the problem that acquiring the lock will move change the cache line into a modified state, and reading the data will how to say, like if you imagine that we acquire the lock and it's a shared lock and multiple backends acquire that lock, or multiple threads acquire that lock, we will, even for reading, we now have to transfer the contents back and forth because multiple backends or multiple cores might have acquired the lock at the same time because it's a shared lock. So we actually, even though it's a shared lock, we constantly move the data around. We will have a lot of cache misses and it will be pretty slow. You can, for example, improve this kind of situation where we spend more time reading data than acquiring the lock by splitting the lock from the read data that's being read, if you have read mostly data, which then will allow the data to be in a shared cache line that will be constantly in all the local caches, and just the lock to be transferred back and forth, which will be better, but only if the lock is held for like not just a very small amount of time, because if it's just a very small amount of time, touching multiple cache lines will be slower. So, but this is like still like a complicated trade-off. We have to figure out how exactly are the access patterns to see whether it's better to split it off. There's other situations where it's like clearer. Like if you look at this scenario, you have two locks on the same cache line and data protected by those locks on the same cache line. If you want to acquire a lock, like you now have lock 1 contending with lock 2, even though they protect separate data, because acquiring one will require transferring the cache line that is also required for the other lock. So this situation you can fairly easily improve by splitting the cache line into two by just saying we'll just waste the space at the end of like the data until like it hits the next cache line by just aligning the data to 64-byte boundaries, and you might have the contention. And often this can be way more than just like a factor of 2. You might, for example, have like, I don't know, just a 4-byte lock and 4-byte data on a cache line that is a lot of contention that can be on that cache line. At the same time, if you just waste that space by like not using it, you actually reduce your cache line utilization, and because of that, you might actually have more cache misses, and because of that, hit more memory. So you have to be aware of like those trade-offs too. And I'm gonna, like, part of the reason to use tools like perf to c2c is to see whether a cache line is actually critical for workloads or whether it's just something, it doesn't matter because it's not a relevant factor for overall performance. An even worse situation is this here. Like you have data lock and perhaps some data protected by a lock, but then you have data that's independent of that lock on the same cache line. And that data is read mostly. Now you have the situation that whenever that read data is that read-only data or read-mostly data is accessed, it will conflict with the lock and have to like interrupt the work that the backend trying to acquire the lock or trying to release the lock is doing. And all the reads will like incur cache misses on their own because like the lock will have transferred the cache line away. And you can see, if you have a bad case of this, you can see massive slowdowns. This is a similar scenario where you don't have to necessarily have a lock involved. Even if you just have like write mostly data and read mostly data on the same cache line, and it's used by multiple execution cores at the same time, that can be being very bad. And you might want to think about reorganizing the data in a way that does not incur this. Another common scenario, and that we have actually encountered a lot of time in Postgres, is that we have data that actually might be aligned with, might be cache line sized, but we didn't take care to align the beginning of the array that contains the data. So we actually now, whenever we access something, we conflict with locks that we don't have to conflict with if we just had like aligned the beginning of the array to some multiple of 64 bytes or 128 bytes. And that can like cost you a lot of performance. And you don't actually save any memory by doing it, because like if you have a longer array, like the bit of alignment memory at the beginning is just like another factor that is relevant for overall amount of memory. So when is this actually a problem to have like this kind of cacheline pattern? Because it's very important to say, like, just because you like find that something is being shared in one of the, or has one of those conflicts, it might be totally fine because like your workload is just not bound by this. It's fairly obvious that all of this becomes much bigger problem the higher your concurrency is. If you have just two cores contending for one cache line, the amount of back and forth will be not a huge problem, because like the rest of the work is probably going to dominate. You can construct cases where you find it like make a huge difference even with two cores, but like you have to work a bit at it. But it's very easy to find ones that like with, I don't know, if you have a 128 core machine, you have to be pretty careful. And if you have like, I don't know, two sockets of 128 cores and you run like a workload that's not very optimized for being well suited for parallelism, it's very, very easy to hit problems. Besides the core number, one thing that matters is like how many internal nodes you have in one socket. The more of these like separate dies you have with the higher latency in between them, the worse it is. And even worse is if you have many sockets in one system. So what can we do about all of this? If you find like an actual problem with it, we can split the data across more cache lines. That's like just waste the space at the end of a cache line, make sure that everything is aligned, and that is often a good solution. But if you do it for some data structure where you have a lot of those units that you're trying to improve the performance of, like that amount of wasted memory can actually be a problem. And the example I'm going to show later will actually have that problem. It often can be good to split the write-heavy data from read-heavy data. And this doesn't have to be like very complicated. Sometimes it's just enough to, if you have a struct with like some state data, to make sure that all the heavily writable data and the heavily read data is like split, like ordered so that like you have that done well. But sometimes it can be worth to make sure that every field has its own cache line, because you have your access patterns. Often it can also be just a good idea to just redesign your whole data structure. That's obviously not as easy as just making sure that something is padded, but it can be often the right thing. If your contention is on just the lock acquisition, and it's very easy to actually contend even just with a shared lock. If you have many backends or cores trying to acquire that shared lock, that will always have to move the cache line around, and that can be quite slow. And that's actually in something like Postgres, where you have buffer locks that is required in shared mode, that can be a real issue. And sometimes you can just get rid of some of the locking. You can reduce the number of times you get the lock. You potentially can cache something to not need some of these accesses. What is perf c2c? It's a tool that detects cache-to-cache accesses, or counts them. And what it really tries to find is that if you access a cache line, and that cache line currently is residing in a different core or in a different CPU socket or whatever, and that current cache line is currently modified, then that's a very strong indicator that you are hitting something that like some other backend also is writing to. And that indicates that you have like some form of contention. It might be legitimate contention, or like it might be you did something stupid like not align your data properly. And that's called like accessing data in another cache that's modified. That's called hitting a modified line. And this perf c2c is available on Intel CPUs, and that's where I found it to be the most accurate. Like it has a lot more detail about like the misses. It finds a lot more of the misses, whereas on AMD, like you can use it and like it works, but like it will not have like as many details. Like you will have to run it for longer to get this like as many details, and some of the things it just can't determine at the moment. ARM is supposed to be really good. I haven't had access to a machine try that. It's generally easier to analyze this kind of stuff on bigger machines. If you have a two-socket machine, two-core machine, it's going to be really hard to find real contention. But you actually can sometimes find problems, even on smaller machines. What you'll often see is that you can find cases of contention on cache lines. It just won't be really performance relevant, but you can see the problem, fix the problem, and then try it at some later point on a bigger machine to see what the performance effect is. But unless you find a very extreme workload, it's probably not going to be a huge performance difference. But sometimes what you can do is to then make your workload more extreme. If you, for example, do read-only pgbench, you might find that you see some some cacheline contention that you can fix, but it won't make a difference. But because the overhead of sending statements from to the server and back, that's too big. So what you can do is, for example, use pipelined pgbench read-only, and that already might make it more extreme to see it, or you might just rewrite it to run the queries in a do loop on the server side, and now you might see it. And that might allow you to validate it on your laptop or whatever, and then later try it without all those workarounds on a bigger machine. Some tips for using perf c2c: it's generally best to compile your binary with fno omit frame pointer, which allows you to use callgraph fp, which stands for frame pointer, because the profile files are just much, much smaller. You can use dwarf, and it will be very accurate, but also instead of a 40 megabyte file, you will have a 12 gigabyte file on a bigger machine. And that turns out to actually slow down things quite considerably. On AMD machines, you really want to increase the sampling frequency, because otherwise you just don't have enough detail. Sometimes using the frame pointer will be a bit inaccurate and will make the profiles harder to read. You occasionally will find that the line numbers are off by 1, or that particularly with inlining, it's a bit hard to read. And for that, you can then use a dwarf in a more targeted way. Just as a rough overview of how a hit looks like, the core will ask its local cache, do you have this cache in this data in your local state? It won't, and then has to go to another core. And often there's complicated systems to figure out which core to ask, or it will just ask all the other cores, and then the other core will look in the local cache, find it in shared or exclusive state, because we're talking about a hit, not a hit on a modified one, and then we'll transfer the data back to the core where we need the data. And depending on whether we actually need the cache line in shared or in exclusive state, it will have to leave the data on the originating side or not. And sometimes that transfer will not happen directly between the two cores, but it will go to memory in between and stuff like that. In contrast to that, a hit M is when the cache line that we're accessing is in modified state, because that has been recently been modified and hasn't been written back to memory. I'll now go to show an example of this, of an analysis, because that's, I thought, the best way to get to understanding how to use it. I initially tried to use the snapshot scalability work as an example, but it just turned out to be too complicated, requiring understanding of too many parts of Postgres to really fit into a talk. So I made up a workload that is simpler. In this case, we just have an accounts table and a transaction table, and obviously there's a relationship between the two, and the query that I'm testing here with is just a join between the two and then doing an aggregation on that. And this is not necessarily the most useful query, it's just something that very quickly gave me a nested loop between the two tables, where you have an index scan on the inner side, where you have a bunch of relatively fast lookups because the index is not huge. And that allows us to see contention on the inner side. How to do this recording? You write perf c2c record. I found that it's almost required to increase the amount of memory that perf can buffer up data before it writes it to disk, because otherwise you will have so many wake-ups that perf disturbs your whole workload with waking up that it's harder to see anything. I found that it's most of the time worth recording call graphs. Sometimes if you have a very big machine, you might want to omit this initially because like it adds overhead even with FP. Depending on what you want to do, it might not be worth measuring the kernel space because like might not be interested in fixing kernel problems. In that case, it's very useful to say -u, which says only track user space. And then you say you want to measure the whole system. It's typically not very useful in the Postgres world to specify a PID here because you want to measure many processes interacting with each other because that's the whole point. You want to measure the contention. On some systems, it works to specify the PID of the postmaster and then only start the workload because it will track all the children of that process. But I found it to be better to run the benchmark into a steady state and only then start profiling and then stop profiling because otherwise it just takes too long and you have too much data. So I just measure system-wide and then you tell it with sleep 3 that should wait until that command is done. And then we can look at the results with per c2c report, and with -d you can tell how it is sorted. For most of the time, on a smaller machine, you want to say tot or local, LCL I think for local, because you won't have any remote memory accesses, so that sorting will not give you anything. On a larger machine with multiple nodes, it can be interesting to just sort on remote memory access because those are the ones that are going to be really, really hurting you. So you might want to look at those first, and that might be different things. So here's how this looks like. Obviously, one of the difficulties I had is like, nobody's going to be able to really interpret this here. So I tried to break it down into like smaller chunks. I initially wanted to do this part live, but I just couldn't figure out how to make it viewable for anybody. So it's stupid pictures that I cut apart. So let's look at the different fields that we have here. The most important one is like total hit mem, which is like how many of the like the modified cache lines in all the cores have we encountered? How many of those were on that cache line that is that's going to be one line below? And then how is that split between local and remote? That's load hit mem when loading the data, and how many stores were there? That's the stores that either hit that were found in L1 or not found in L1. And if you have a store that's not found in L1, what that often means is that the data in between reading the data for like a +1 or whatever and writing it out had been already transferred to something else. So that can be like a warning sign of that something is like really heavily contended. Or it can be something else, but too complicated. And then core load hit is just like, how was the access on the local, how many accesses were there locally on the current CPU core, and then was the data found like in the LLC, which is like the L3 cache, locally on a different machine. It also shows you how many were found in memory. That's not really interesting for analyzing contention that much, but it can still be interesting to watch just to find problems where we have like our cache access patterns are really bad, or memory access patterns. Here's the first part of like running this workload on, I think this was on my workstation. And what you can see is that for the hit mems, like there's really just 2 cache lines where just almost all of those are. And we have a pretty simple workload here, but that shows you that we have a very clearly a problem because like the accesses are very narrowly distributed. So you can, if you improve anything on those 2 places, you're going to improve the overall performance of the workload quite substantially. I have never actually figured out what PACNT means. I think it means something like physical addresses, but I think the number is just plain wrong. I tried to figure it out. I got lost after a couple of hours and had to move on. The other part of this overview is here that it will show like how many of the stores and so on were in different parts. Here we can, like, it sometimes can be interesting to look at if you have like something like this here, it will, it's interesting. That means like where we have very few local access and a lot of remote accesses, that might mean that you have to be careful about distributing your data more across a wider area of memory so that you don't have as many remote accesses. In this case, I think all the memory was located on one CPU socket. So everything running on the other CPU socket had to be a remote memory access, which is bad, particularly if your cache hit ratio is low. If you press D, while being on one of those cache lines, and you can just navigate those with up and down cursor, you'll get like a detailed view of just the cache line. And that's really where you can get most of the value. Because one of the most crucial part is probably that it tells you here under offset, at which offset in the cache line was this access, and which then typically means that you can figure out which field you were actually accessing, and that can tell you like, did you have like a lot of read accesses at this offset, and then another offset, did you have a lot of write access, and that will tell you that you have contention between read and write accesses. For example, here we can see that there, we're basically no store references because all of these are 0. So we can infer that this was a read-only access, which then indicates that it's like read-only. If you'll see later an example for where there was a write. And at the end, it will also tell you from which source code line actually triggered this, and that will allow you to infer like a bit more about the context by looking at that up. Here, the CPU count is actually pretty useful too, because it will tell you how many CPUs were entering this access pattern, and that is useful to detect cases where like you have data that is like only used by one CPU, but then you have multiple of that pieces of data on one cache line. What you then see is the typical pattern that like one offset, one CPU, another offset, one CPU, and that tells you that you have a problem with having state on one cache line that is like accessed very, very differently, that shouldn't be shared, but is required to be shared between all the cores, which is good for read-only access, but not good for write accesses. So I'm now going to just look at if you go back here, first going to analyze here the second cache line, because I'm not going to go into as much depth. So these are all the accesses in the second cache line. You can see that we had no stores on the first from this access pattern, but we had stores here, and that all of those access patterns were for the same offset. And the reason that there are multiple entries is just that the symbol here is actually like that it's called from different places. You can also make perf c2c collapse everything based on the offset, but then you lose information about the callers. So it's typically more interesting to do it this way. And this, if you look at it, like we can see that it's all LW lock, so locking related stuff, and which indicates we are dealing with real lock contention here. So the next thing to do is to like fold out like the callers here, and by hitting plus, and you'll see something like, hello? Like this, which will tell you what the callers are. And from the cache line perspective, you can't really do something like split the work up over multiple cache lines, because it's a single lock, you can't do that. So if you want to improve this, you would need to improve the actual locking. In this case, it's actually kind of easy. I'm not going to do it here because there's actually a patch on the mailing list already, I think. The problem here is that this is the root page of the B tree. And every single access, every single scan will access that. But it actually barely ever changes. So you can actually get rid of, like cache more of the data, and that will relieve a lot of the contention. There still needs to be some coordination of it so it doesn't completely vanish, but you could just get rid of that lock and make things a lot better. This is the best kind of thing. Like you can just get rid of the contention by like not doing it, and you'll be much better off. Now I'm looking at the first cache line where most of the contention was. Maybe anybody already can see like some interesting pattern here. I don't know, maybe after a few seconds. Not, I can just go on.
Is it scanning the buffers?
No, like we can see here that like the first few accesses are on one cache line, then another cache line, and all of these here, there's no stores. And then here later on like the other offsets, we do have stores on like from some of the callers here, right? Which means that these are modified, and these are modified. This offset is modified, but this part here is not. And then if you look at the callers, all like this here, buffer get rel number, like buffer get block number. That sounds like a read-only access. And then if you look at the caller of this one here, we'll see that actually this is something, it's also read-only access to the block number. And the next access is also something just a read-only access to the buffer ID. And a read-only workload that fits full into shared buffers, there's never going to change. And now we can look at the underlying data structure here. We have, this is the output of PA hole, which gives you like the layout on disk or in memory, like the structure layout, including padding and so on, which is, I find very useful for analyzing some of this kind of thing. And you can see that at the beginning, we have the tag and the buffer ID, and those are going to be like almost read-only, unless you have like a workload that constantly replaces contents. Wait backend PID, backend POCNO is also extremely rarely modified in most workloads, and Phoenix as well. But in between, so we have a heavily modified one. This is the state, which is like modified whenever you pin a buffer, you have to increase the pin count. And then the content lock, whenever you lock the page, you have to modify the lock. So what we have the problem here is that we have very heavily modified state and read-only state on the same page. And it turns out that we access, like those read access are actually fairly frequent, and those heavily contend with the locking, and both sides are really slow. If you go back, damn it, I cut out the important information. Oh no, here. Here will actually show you the approximate number of cycles that one of the accesses takes. And if you can see, like, it's never a good sign if one of your read-only accesses takes like 3,000 cycles. That's obviously incredibly wasteful, and like nothing is going to perform well with this. So what could we do here? Like, there's a very easy fix here. What we can just say is like, okay, we'll move the state at the end of the other things, and then just increase padding after the read-only fields, and then add some more padding after the state, so that the read-only data that is on one cache line, the state is on one cache line, and the content lock is another cache line. Obviously, that has problems. This is a quick and dirty fix. That's not a real something that we would necessarily want to do, because we're going to waste a bunch of memory, because this is not going to use a full cache line. This is just 4 bytes, and this is, I think, 8 bytes, 12 bytes, something like that. So this is not very memory efficient. But it should address our contention problem, because now we don't have this false sharing, and we actually improve the locking overhead as well, because we have like the contended lines for 2 parts split out. And indeed, if I run this on, even on my laptop, I actually see good performance if I use improvement with 16 clients. This workload goes from 7,500 to 10,000 transactions. For like a 5-line change, that's a pretty good scalability improvement. And wasn't that big a change. What we also see is here that we get a small slowdown at 1 client count. I think this is not noise, but it's close to the amount of noise, so I'm not entirely sure, but I think that's just that the cache head ratio goes down because we have used more memory. If we could totally improve this thing by, for example, saying that we put now the read mostly state, like the buffer tag, we put 2 of those on for different buffers on the same cache line, because they're like read mostly, so there's not going to be any problem for contention or anything. In contrast, we actually make it faster, because like that data, we have now higher cache density, and that would probably get rid of this small regression. I haven't tried it, but on my workstation, you can see that the before performance is extremely bad. Like, even though it has like a good bit more cores, it's like a third or so of the performance. And what we see here is basically that what we're currently doing scales extremely badly, and because of that, it scales really bad on a bigger machine. It's also the case that like this laptop is like half a year old, the workstation is 5. So like both of those play a role, but like in other workloads, the workstation beats my laptop hands down. But this one is really bad because we have so much contended access on like a small number of buffers, and that just kills you. If you get rid of that locking thing for the root page, the workstation gets a lot closer, but it still doesn't quite catch up. And I think that's mostly the CPU architecture stuff. So what caveats are there to this kind of thing? Most of the time, you're not going to immediately see a benefit as big as like 1.43x. This problem here that I analyzed, I initially found this with PGBench-S, and I was actually somewhat surprised to see this problem. And I initially started trying to look at fixing it, and my initial thought was, it's completely stupid that the B-tree code and various other parts use buffer get block number. We could just avoid this problem by not making them use buffer get block number, then we wouldn't have all those read accesses. But it turns out we have been lazy and used this in a lot of places, and some of them are kind of hard to fix. So I think it might be better fix to fix this on a data structure level. The reason that I didn't end up choosing this PGBench-S for this is that on a laptop, I wasn't able to reproduce this as a problem, and I thought it would be nice to have something that can easily be done on your normal dev box rather than something larger. On my workstation, I can already see the effect of PGBench-S, even though it's for a 2-socket machine, it's fairly small. But only I think without pipelining, it's in the 2% range, and with pipelining, it's 15%. On a larger machine, it's a 1/3 improvement for PGBench-S, which is something that's actually generally pretty hard to get to. So I think it's something we should fix, but yeah. And with that, I'm open for questions.
So, when I learned to write algorithms and stuff, it was back when they talked about big O and avoiding n squared stuff. I assume there should be some new algorithm education that says, here are all the cache efficient algorithms you use. Here are all the old algorithms you should stop using in the 90s. Do you have a recommendation of a reference like that?
I haven't found a very good reference, but it's also because I hadn't looked very much, so I wouldn't expect to. I mean, you can, I think generally in the 90s, you would have read a lot more use of linked lists and stuff that we now know is very bad, but that's kind of independent of contention level issues. Is just bad because of memory latency being high, and memory latency not having reduced much compared to CPU speeds. There's a bunch of random stuff, but I don't know how much this is actually something that has really gotten back into academia. I found this is much more, I think, on the practitioner side of things. There's papers that talk about contention-friendly data structures. And for example, around blocking, there's a lot of actually stuff that writes about how to design blocks that scale better by partitioning some state across multiple cache lines and stuff like that. There's also a bunch of other, around the lock-free data structures. There's a lot of analysis of this because that's how you end up scaling.
While I recognize the point of this was to educate us and so you don't have to look for all cache line contention, I have a specific question about the solution that you proposed. So you...
No,
you were make the buffer descriptor fatter, which not that, but then at the end you were actually, let's not do buffer get block number everywhere. So can you?
No, I don't think that's the proper solution by now anymore. Well, that was my first attempt, and it burned because there's so many.
Okay, well, I was going to ask if you would talk more about that, but
I mean, we can get rid of buffer get block number in a bunch of places, but we also have
how? What would we do instead?
I mean, most of the time, those places already know which block they're looking at, right?
Yeah, okay.
It's kind of it's just laziness, basically. Okay, I don't know, B-tree code literally has code where it's read buffer, but it does it one level down, and then 2 lines later, it does a buffer get block number.
Yeah,
it's
or
just
it could have passed it as a parameter and it just didn't, or whatever.
Yeah. So a lot of that, but I don't think it quite's gonna suffice because there's also stuff the buffer tag, and if you imagine that you have lots of lookups in the buffer mapping table, they're all gonna look at the buffer tag eventually, and so on, and then you get contention because that pulls it back and forth, and so it's probably better to just do this on a data structure level.
So I think this is pretty much what you're saying, but I just want to clarify. So the reason you would add the padding afterwards is because there's no way for something else to access that. So there's no artificial contention that's done. And then if you have a lock and you have the data that's correlated with that lock on the same cache line, then there's no issues because it's literally protecting that data. And so if you modify it, you want the updated data anyway. Is that
yes,
correct?
with one caveat on the last part. If you have locks that are held for a while, then that doesn't hold true anymore because even the accesses to the correlated data or that it belongs together, there might be other lock acquisitions in between. And the longer you hold the lock, the more likely that becomes.
Are there situations where there are correlated locks where it's fine to have like two locks on the same cache line?
That reminds me of a very important point. We don't actually want to go and just pad everything because that will be very bad for performance because we will just hit memory more often. So you shouldn't start by padding everything. That's kind of why it's very good to be able to use something like perf c2c, which will tell you whether you have actual contention. And then you know, okay, this is worth improving. Sometimes it's obvious. Like, I don't know, if you have a wall insertion lock or something where it's one of the most central pieces, like performance pieces, then you don't need to necessarily measure it first because but yeah.
Yeah, so I noticed that our definition of cache line is 128 bytes rather than 64, which you say is the most common configuration.
Yeah, but it's also not uncommon to use 128.
So is it not worth to have like two builds, one with each and select the...
I think it might have actually been more worth a few years back, but now we have complicated things where I think some of the big little architectures with fast and small cores actually have different cache line sizes, and stuff like that makes it really hard. And it doesn't necessarily hurt, depending on the use case. I think we have because we define it to be 128 bytes, we actually have some parts that intentionally ignore it, and then use a hard-coded 64. And I'm guilty of this. Just because there are places the wasted would better. But in other places, I don't know, if you pad each wall insertion lock to 128 bytes, it's never going to matter because it's not a lot of memory. I don't know whether it's worth improving.
Can you use the same c2c perf also for investigating a single process cache usage? For example, I timed the new Radix code and it looked like adding timing had less impact when the lookups were faster. So, which is kind of counterintuitive. It looks like it's some kind of cache issue, but how to figure it out?
You can. It's not it's sometimes just useful. It doesn't. One problem is that perf c2c doesn't offer you to sort on anything very useful because it sorts by hit mem by various places, which you're not going to have as much if you have a single process, a single execution thread. There is perf mem, which basically is perf c2c uses perf mem under the hood, and that can give you actually a lot more detailed stuff for some of this, and that might be useful to see. And it also has at least on Intel, it has latency information for the individual accesses, so that could help. And actually, you can use perf mem report on a c2c record output, and it will still be useful. Sometimes it's useful to do a c2c report and then afterwards use perf mem to look into more detail, all the different accesses, not just the hit mem accesses. One more detail is that perf c2c report, you can give it -- stats, and that gives you just some top level stats that can sometimes be interesting to look at. I think we are running out of time.